Good morning. Today we are going to see the last point of unit number 4, that is the solar PV cells, its working, its construction, and also the applications. Okay. It will be only a descriptive part, its characteristics, current voltage characteristics, and its applications, how it is constructed. All those things only the descriptive part will be there for your exam. Okay. In last lecture, we saw the thermal energy storage system, and we can divide this storage system into two types: sensible heat storage system and latent heat storage system. In the case of sensible heat storage system, we are seeing that by increasing the temperature of substance, we can store the heat. Okay, so that stored heat during the daylight, it has been used during the night time. Okay, because the sun radiation is not constantly incident on the one particular location on the earth. Because of the rotation of earth, there will be a changes in the solar radiation received by this particular point, and that's why we have to store that energy. So it will be stored when it is available, right? So during the daytime, this radiation energy or the solar energy is stored in the form of heat energy, and that we can use. Now, sensible heat, we are increasing the substance of heat during daytime, and during night time, we can reduce its temperature. We can uh, extract the heat from that particular substance by reducing the temperature. That is sensible heat storage system. The latent heat storage system is related to the phase change of the material. Now, the big difference between these two, you already know the difference between sensible heat and latent heat. During the latent heat, there will be no any temperature change. So at constant temperature, we can get the heat whenever we use the latent heat storage system. So these two types, its introductory part will be there, and also the different types of the this type of storage system. I will share the PDF to you on our Moodle. Okay. Now next and the last point of this chapter is that solar PV cell. Okay. It is also called as a solar photovoltaic cell. Now, solar photovoltaic cell is an energy harvesting technology. Means we are used to extract the energy. Now, these solar PV cells will convert the radiation energy of sun, which is received from the sun. It has been converted into the electrical energy. Okay, so that is the main function of solar PV cell. So it will convert the solar energy into the useful electricity or electrical energy through the process, which is also called as a photovoltaic effect, and that's why it is called as a solar photovoltaic cell. Now there are several different types of the PV cells we can use. The main material we are using in this in solar PV cell, the construction of solar PV cell, it is known as a semiconductor, and particularly in most of the PV cells applications, we are using silicon semiconductor. Okay, because of its characteristics, because of its properties, we are generally use these silicon as a construction material in the solar PV cells. Nearly 90 to 95% solar PV cells or the cells has been manufactured by using the silicon semiconductor nowadays. Okay. Now, the main hurdle, or we can say the disadvantage of this particular technology is that the construction cost. Whenever we construct or manufacture the solar cells, it has contain very high construction cost, because extracting the pure silicon from simple sand, it is very difficult process, right? The sand is available, but the extracting the pure silicon, it is very difficult. Okay. Now for construction or manufacturing of this PV cells, we require pure silicon, and we cannot achieve in less cost. So the total manufacturing cost of the PV cells is very high, and when we compare it to the normal thermal power plant or any other conventional power plant, the cost related to the generation cost related to these solar PV cells and that particular conventional resources, the difference is very big. Okay, we require the manufacturing cost, or we can say the generation cost related to the solar energy is much higher than the conventional power plant. So that is main hurdle in this particular technology. But nowadays, what will happen because of the mass production and other factors, the manufacturing cost is goes on decreasing. Okay, and because of the development of technology to extracting the pure silicon from the sand and all those things, these particular cost of that PV cells is going to be decreases. Now you will see what will actually happen. The sunlight will incident on the solar cell. Solar cell will convert that into the electricity, directly convert it into the electricity, not in any type of chemical energy or any type of mechanical energy. It will directly convert that energy, sunlight energy, into the electricity, and that electricity we can use for any particular applications, or we can store that electricity. We can use that electricity later on, whatever you can do. Okay, but nowadays the solar PV cells and use of solar PV cells has been increasing. Even in India, you will see the solar cells using use of the solar panels has been increasing, and the generation of the energy through the solar panels is going to be increasing. Okay, so that is the main effect you can see. Now the construction, regarding the construction, as we know, the main basic block or the basic construction material is the semiconductor, any type of semiconductor, and generally we are using the silicon. Okay, now this particular construction of the PV cell, I will show you one video so you will easily understand how it has been constructed, what are the different parts, what is P type of semiconductor, what is meant by N type of semiconductor, how they are connected and why they are connected, then what is the bridge between those two semiconductors, and how the current is passing. So likewise, those all construction and that particular one, I will show you one video so you will understand. Before that, you must know what is the differences. Okay, differences between solar cell, solar module, and solar array. Because generally in manufacturing sector or during in the solar sector, you will heard these type of the terms many times. Okay, so first of all, what is meant by solar cell? Solar cell is means it is a single cell. Okay, as the name indicated, it is a single cell which is having P type of semiconductor and N type of semiconductor, and it has been one singular cell. Okay, now, when we connect numbers of solar cell in series and parallel collection, then that total particular display or that particular the bunch of or the group of solar cells is known as the solar module. Okay, so that is the difference. Solar cell is a different one. It is the main fundamental part, and the when we connect that solar cells, the many numbers of solar cells in series and parallel, it is called as the solar module. Okay, generally you are generally saw this type of the display or the solar PV panels. So it is also known as the solar module. And when we connect this solar module in series and parallel, when we arrange it in the serial and parallel connection, that total display or that total panel is also known as the solar array. And these type of solar arrays you are generally saw where the more amount of energy has been generated through the solar cells or the so different types of the solar parks. You will see this type of array. Okay, so that is the difference between the solar cell, solar module, and solar array. Because you will get confused between these three terms, because sometimes for all the terms we are only using only one particular name, that is solar panel. But solar panels, it is a generalized term. If you saw, the solar cell is a different one, solar module is different one, and solar array is a different one. Okay, the numbers of cells when we connected, it is called as a solar module, and when we combine the numbers of solar modules, it is called as a solar array. Okay, so that is the solar difference between solar cell, solar module, and solar array. I will just show you one video of the construction and the working of PV cells, so you can easily understand how PV cells has been working, okay, how those are constructed, and why it is very difficult to manufacture these solar cells. Okay, so that you can understand. Just I will play one video so you will understand it. Just tell me,
अरे
can
यानंतर
you hear this
ग्रोसरीज
video?
मग डिशेस मग लॉन्ड्री
Just
मग
भावा
reply.
बंद कर ही
Can
लॉन्ड्री
you
लिस्ट.
hear this
आधी थोडा संडे करून घेऊया.
video?
अरे संडे संडे
The
संडे
audio is
संडे
हा झाला ना
the audio is
संडे.
clear.
संडेचा दिवस बनला.
मनाला मॅगी मॅगी करून गेला.
Can you please reply?
This means in the last 2 decades, the country
Please reply. Is anyone? Can you
Contribution of solar energy to the world's total energy supply
Can you
has
share
grown
the video?
significantly.
Okay.
This video will show how solar cell or photo
I will just see this video. You will understand the working construction, how the solar PV cells are manufactured, and why it is very difficult. And you will understand the working of the PV cells. Okay. So I will just play this video. You will understand the working.
energy to the world's total energy supply has grown significantly. This video will show how solar cell or photovoltaic cell produce electricity. Energy from the sun is the most abundant and absolutely freely available energy on planet Earth. In order to utilize this energy, we need help from the second most abundant element on Earth, sand. The sand has to be converted to 99.999% pure silicon crystals to use in solar cells. To achieve this, the sand has to go through a complex purification process as shown. The raw silicon gets converted into a gaseous silicon compound form. This is then mixed with hydrogen to get highly purified polycrystalline silicon. These silicon ingots are reshaped and converted into very thin slices called silicon wafers. The silicon wafer is the heart of a photovoltaic cell. When we analyze the structure of the silicon atoms, you can see they are bonded together. When you are bonded with someone, you lose your freedom. Similarly, the electrons in the silicon structure also have no freedom of movement. To make the study easier, let's consider a 2D structure of the silicon crystals. Assume that phosphorus atoms with 5 valence electrons are injected into it. Here, one electron is free to move. In this structure, when the electrons get sufficient energy, they will move freely. Let's try to make a highly simplified solar cell only using this type of material. When light strikes them, the electrons will gain photon energy and will be free to move. However, this movement of the electrons is random. It does not result in any current through the load. To make the electron flow unidirectional, a driving force is needed. An easy and practical way to produce the driving force is a p-n junction. Let's see how a p-n junction produces the driving force. Similar to n-type doping, if you inject boron with 3 valence electrons into pure silicon, there will be 1 hole for each atom. This is called p-type doping. If these two kinds of doped materials join together, some electrons from the n side will migrate to the p region and fill the holes available there. This way, a depletion region is formed, where there are no free electrons and holes. Due to the electron migration, the n-side boundary becomes slightly positively charged, and the p side becomes negatively charged. An electric field will definitely be formed between these charges. This electric field produces the necessary driving force. Let's see it in detail. When the light strikes the p-n junction, something very interesting happens. Light strikes the N region of the PV cell, and it penetrates and reaches up to the depletion region. This photon energy is sufficient to generate electron-hole pairs in the depletion region. The electric field in the depletion region drives the electrons and holes out of the depletion region. Here we observe that the concentration of electrons in the N region and holes in the P region becomes so high that a potential difference will develop between them. As soon as we connect any load between these regions, electrons will start flowing through the load. The electrons will recombine with the holes in the P region after completing their path. In this way, a solar cell continuously gives direct current. In a practical solar cell, you can see that the top N layer is very thin and heavily doped, whereas the P layer is thick and lightly doped. This is to increase the performance of the cell. Just observe the depletion region formation here. You should note that the thickness of the depletion region is much higher here compared to the previous case. This means that, due to the light striking, the electron-hole pairs are generated in a wider area compared to the previous case. This results in more current generation by the PV cell. The other advantage is that due to the thin top layer, more light energy can reach the depletion region. Now, Let's analyze the structure of a solar panel. You can see the solar panel has different layers. One of them is a layer of cells. You will be amazed to see how these PV cells are interconnected. After passing through the fingers, the electrons get collected in bus bars. The top negative side of this cell is connected to the back side of the next cell through copper strips. Here, it forms a series connection. When you connect these series-connected cells parallel to another cell series, you get the solar panel. A single PV cell produces only around 0.5 voltage. The combination of series and parallel connection of the cells increases the current and voltage values to a usable range. The layer of EVA sheeting on both sides of the cells is to protect them from shocks, vibrations, humidity, and dirt. Why are there two different kinds of appearances for the solar panels? This is because of the difference in the internal crystalline lattice structure. In polycrystalline solar panels, multi-crystals are randomly oriented. If the chemical process of silicon crystals is taken one step further, the polycrystalline cells will become monocrystalline cells. Even though the principles of operation of both are the same, monocrystalline cells offer higher electrical conductivity. However, monocrystalline cells are costlier and thus not widely used. Even though running costs of PV cells are negligible, the total global energy contribution of solar voltaic is only 1.3%. This is mainly because of the capital costs and the efficiency constraints of solar voltaic panels, which do not match conventional energy options. Solar panels on the roofs of homes have the option to store electricity with the help of batteries and solar charge controllers. However, in the case of a solar power plant, the massive amount of storage required is not possible. So, generally, they are connected to the electrical grid system in the same way that other conventional power plant outputs are connected. With the help of power inverters, DC is converted to AC and fed to the grid. Please support Learn Engineering's educational activities on patreon.com. And also, don't forget to subscribe to our channel. Thank you.
Okay, so you understand the working of the solar cell,
This means
how the
that,
solar
due
cell
to the
is
light striking,
working, and how those are going to be work, and what is the PN junction diode, and and other things. Okay. Then the another thing is important is difference between solar array, solar module, and the solar PV panel. So just see this another video so you will understand and how those are going to be
In
connected
first
in the
industrial
circuit.
revolution,
So
wealth
we will
went from
understand
farmers
how
to factory
those are
workers.
different
In second
and each other,
So I
and what
think
are
that's
the
enough. You
differences, how those are connected to each other in series and parallel connection. Okay, just see this video.
need to know about materials. At least you have a bit of an idea which kind of options there are. Now let's look at how you can take the individual solar cells and combine them so that you can actually form a solar photovoltaic module. So if we are creating a solar system and we're going from small to big, then we start with a solar cell. If we wire several solar cells together and place them into one frame, then we have created a solar module. If we now combine two or more solar modules together into one rigid frame that comes pre-wired out of the factory, so from the supplier, then we have created a solar panel. And then if we combine several of these pre-wired solar panels together into one overall system, we have now created a solar array. But these are just words, so let me explain it a bit easier by giving you some visual materials or photos of what the 4 different steps actually look like. So let's have a look first at the solar cell. So what you can see here is a polycrystalline solar cell like we discussed before, and I want to point out 3 different components of the cell. So we'll look at the fingers, the bus bars and the connectors. So the first one, the fingers, are the very tiny, narrow strips of conductive material which are attached on both sides of the solar cell. And then the fingers, they collect the power from the solar cell, redirect it through the bus bars, which are the larger kind of conductive material that are attached to the surface of the solar cell. And then, of course, you want to connect the solar cell to other solar cells. So at the end of the bus bars have the connectors where they are welded together with the other solar cells. So now you understand what a solar cell is. Now, if we combine all the solar cells together, then we are creating a solar module. This is probably something you easily recognize. And here you can identify the individual components, right? You have the solar cells, you have the bus bars connecting all the cells together, you've got the frame around it and the backing sheet. So this is a solar module. And if you would closely look at this photo, you'll be able to see that all the cells are kind of connected all together in one long string, in one kind of a long snake, right? And the head and the tail of the snake, this is where the bus bars go through the panel, and on the back side of the panel, that's where the two wires will be connected to. Now you can see the individual solar cells in this module, but there's something interesting in the way that they connect all the cells together. So if we zoom in a little bit more, you can see how they actually connect one cell to the other one. Because it seems like cell number 1 is just directly connected to cell number 2 through the main bus bar. But if you look more closely, you can see that actually the top of cell number 1, the bus bar, is actually folded under cell number 2 and then connected, well, you can't see it, but there it's connected to the bus bar at the bottom of cell number 2. And then the current runs from the bottom of cell number 2 through the solar cell up to the top. And then again, the bus bar at the top of cell number 2 collects the electricity and just sends it through again to the bottom of cell number 3. And it just continues like this throughout the whole solar module. Okay, we're going a little bit in detail here, but I like to explain things and you're here to learn, right? So now you fully understand how the wiring runs throughout a solar module. Now let's have a look at the basic components from a module. So let's take a theoretical solar panel and just pull all the layers apart so I can name each and every layer individually. So this is not rocket science. You first have the frame, then you have the glass cover, you have the encapsulant, then you have the actual solar cells themselves with all the wiring there, then you have another encapsulant, the backing sheet, and then all the way on the back you've got the junction box, which is normally glued on the backing sheet. Alright, let him shut up for a second. I just want to explain to you that the content of this video is copied from the complete course of off-grid energy systems. If this information is enough for you, great. If you want to learn more and if you want to get access to the complete course, then check the information in the description below. Alright, you go ahead again. Okay, so I think that's enough for solar modules. You fully understand now the different components, how they're wired together. Now let's briefly look at a slight variation of the solar module, which is the solar panel. So the proper definition of a solar panel is more than one photovoltaic module which are mounted together on one solid frame and they're already pre-wired by the manufacturer. So this is actually a solar panel. Now, this being said, you know now the difference between a module and a panel, but most of the time people refer to both the modules and the panels with the word of photovoltaic panel or solar panel. So now that you understand the difference between a cell, a module and a panel, let's look at what a solar array actually is. So a solar array is a combination of several modules or panels that are all connected in series. So they're all connected head to toe with each other. And this solar array is often referred to as a string, as one string of solar panels or modules. This is being done in order to increase the overall operating voltage of the system. So the typical voltage that you will see for one array is somewhere between 500 and 1500 volts direct current. Alright, so now that you understand all of this, now let's look at the last section on connections, and I want to look specifically at junction boxes and the external connectors, so the wires that come out of solar panels.
Okay. So that is the difference between the solar cell, solar PV cells, solar module, and solar array. Now, next point is the last point of this chapter is that is regarding the IV characteristics, or we can say the current voltage characteristics. You can see the graph of IV characteristics. Okay. Now, you know the current which is developed by the solar PV cells is depends upon how much amount of radiation it has been incident on that particular panel. Okay, and based upon that, the radiation intensity is going to be changed, and as radiation intensity is going to be changed, the voltage or the current developed by these PV cells is going to be varied. Okay, now we know the power from the particular panel is equal to voltage into the voltage into the current, right? It is the multiplication of voltage and current. Now you can see the IV characteristics of the PV cell, okay, or the PV panel. You can see this blue line that is the passing from the short circuit current to the open circuit voltage. You can see this blue line. It will indicate the characteristics of the PV module or the PV panel. Okay, so means if we consider the current produced by that panel, it is around this at this particular position, at this particular point, then the voltage generated by that particular module, it is near about this point. Okay, and if we saw when the panel which will produces the very high current, okay, current will be the very high in that case, and at that time the voltage, the value of voltage is the less. Okay, so current is very high, which is produced by the panel, and voltage is less. Means voltage is there about 1 to 2 volt, and current is in amperes, 100 to 200 amperes, etc. Okay, so you will see the intensity of the current is more and the voltage is less. As we increases the voltage at after some point, if you consider from this particular point onwards, the intensity of the current is going to be changed. Means if we increases the voltage which is developed by the panel, in that case we lost the current. So because of that, what will happen? The power is going to be lost. Means we know power is equal to voltage into current, right? Voltage into current. So when we the whatever the power which is generated by the solar panel, it is based upon the voltage as well as the current. Okay, so when any of this particular point, the quantity is going to be decreases or increases, it will going to affect the power. So if you saw, if we increases the voltage, okay, if we increases the amount of voltage generated by the PV cells, in that case we lost the current, and it is alternatively we lost the power. So we have to find out one particular point at which the power produced by the panel is maximum. Okay, the one operating point where the power produced by the panel or solar array should be the maximum one. Okay, so in that case you will again see the graph of the power with respect to the voltage and current. You will see from the initially amount of current from 0 point, the power is going goes on increasing because the current and the voltage is going to be increasing. Current is generally constant. As after this particular point, the current is decreasing, sharply decreasing, and because of that, these after the maximum point, the power is going to be decreasing. So if you saw this maximum power point, okay, this point, okay, this maximum power point, it will at where the maximum power will be generated, and the current as well as the voltage related to this that particular point is known as the maximum power point voltage and maximum power point current. Now it is desirable that the particular solar panel must work at this particular point. Okay, means the characteristic that particular panel must be work or must be generate the voltage at that point and the current at that point. Okay, so for that sometimes what we do, we are using MPPT, maximum power point tracking device. Okay, so what it does, after this panel we are installing that MPPT, and it will convert the values of voltage and the current such that we will get the maximum power from that particular panel. Okay, because the whatever the current and voltage generated by the panel, it is depends upon the radiation, okay, conditions of the radiation, right? Or the condition of weather, etc. So when the radiation intensity is going to change, the voltage and the current generated by that panel is going to be changed, and to get the maximum power, that voltage or the current value is going to be changed by the MPPT, maximum power point tracking system, and it will achieve, or we can achieve, the maximum power. Okay, so just see another video, so you will understand the working of the MPPT and why it is important to get the performance of the to improve the performance of the PV cells or the PV model. Okay, just see this video so you will understand it.
पहले नंबर पे कौन आएगा?
पहले नंबर पे
अन्वेषण।
अन्वेषण आएगा।
Okay, I think we have talked enough about the PWM charge controller. Now let's look at the more advanced type of solar charge controller, which is the MPPT, the Maximum Power Point Tracking Solar Charge Controller. Now these type of charge controllers are quite advanced, they're quite intelligent, but it's actually not that difficult to explain how they work. So the key feature of MPPT charge controllers is that they have two different kind of circuits inside of the charge controller. One on the side of the source, one on the side of your solar panel, and the other one on the side of your load, on the side of your battery. You could therefore describe this kind of solar charge controller as a DC to DC converter. It takes the DC power from the solar panel and converts it into a different kind of DC power that it sends towards your load, towards your battery. So let me try to explain this a bit better with a simple drawing. So we start with a solar panel that you connect to your MPPT solar charge controller, and on this side of the circuit you most of the times have a high voltage, a relatively low amperage, but you're right at the right spot on the solar panel, so you're right on the maximum power point of the solar panel, and the solar panel is producing as much power as it possibly could under the given conditions. And now you're connecting the MPPT charge controller to your load, to your battery. And on this side of the circuit, often you have a much lower voltage, therefore a higher amperage. And most of the MPPT solar charge controllers have a relatively high efficiency. So up to 100, well, up to 99 point something percent of the energy that you took from the solar panel, you're actually sending that towards your load, towards your battery. So just remember that MPPT charge controllers have two different circuits, one on the side of the solar panel, which most of the times works at a relatively high voltage, and a secondary circuit which works on the side of your load, on the side of your battery, which works on a much lower voltage. So let's also look at the IV curve and let's see what happens to the voltage and the amperage if you connect a solar panel to an MPPT charge controller. Alright, let him shut up for a second. I just want to explain to you that the content of this video is copied from the complete course of off-grid energy systems. If this information is enough for you, great. If you want to learn more and if you want to get access to the complete course, then check the information in the description below. Alright, you go ahead again. So a first look at the situation where the sun is high at the sky and we've got a nice IV curve with a high amperage and voltage. So if you connect this solar panel then to the MPPT charge controller, the MPPT charge controller will actually adjust the voltage and will walk along this line until it has found a point whereby the voltage times the amperage results in the highest power output. And once it's found that sweet spot, it will stay right there and you get your maximum power output from your panel. And then if the conditions would change, so for example the sun would start to go down or you would start to get some cloud, some overcast, then the curve would change, but the MPPT charge controller would do the same again. It would adjust the voltage and would walk along this IV curve until it has found a point on the curve whereby the result of voltage times amperage is a maximum, and again under those conditions, the MPPT charge controller has found the maximum power point on the IV curve, so you're getting the maximum power out of your solar panel for the given conditions. Alright, so we're almost done because by now you understand what an IV curve is, you understand the basic functioning and the possibility.
So that is the meaning of the IV curve and MPPT, okay, maximum power point tracking. So that is the details regarding the solar PV cells, how it is manufactured, constructed, and what are the materials we are using. You already saw. I will share this PPT. That is the end of our chapter number 4, that is solar energy. We saw the different introduction to the solar energy, the detailed introduction, then the detailed solar geometry, and also the radiation data, then the different types of the collectors, the different types of the thermal energy storage systems, just an introduction part, and then the operation principle of the photovoltaic cell. So these are the related to the solar energy, and by using those systems, we can convert that solar thermal or thermal energy or the radiation energy into the useful energy. Okay, so that is regarding the solar energy. You can refer uh, the solar energy book by the S.P. Sukatne, in which in details you will understand the solar geometry, what are the potential types, and all those things. Okay, and also from the next lecture onwards, we are going to start the wind energy chapter, chapter number 5, in which the introduction of the wind energy is given, the different models, power output from the wind, site selection, those generalized systems, wind energy conversion systems, different windmills, etc. Okay, so that is regarding the unit number 4. I will share this PPT. Also, I will share the video link, the links of the recorded lectures, so you can understand, you can study this particular chapter. Okay, so we will stop here. If anybody